So good morning, everyone, and welcome to this 17th session of Memory Design and Test course. So before we start, I just want to know how are things with all of you, and let us do a quick refresh of what we were doing in the last class. So please.
So we looked into the DRAM, like the basic DRAM, uh, uh, basic read and write. After that, the dummy read, that is a refresh. Then we looked into the capacitor, like how there is one transistor and one capacitor. So how that capacitor can be designed. So some different types of designing of capacitors. Then we looked into some timings, few timing diagrams, like early read and early write and late read, late write. And after that, yeah, that's it, I guess.
That's it. So how is the DRAM organized? Who will tell?
It's in the squarish manner.
Why is this array a square always?
Same
To
number of
like
column and rows. Same number of column and rows will be there.
Yeah, why is that a requirement? That's the question.
Because
for easy
DRAM,
decoding,
Hmm?
to make decoding easier.
Decoding easier. How does it make it
Like
easier?
less pins. Uh, yeah,
that
like we were sending 11 bits for row, and after that we were sending 11 bits for column. So but usually we had to send 22 bits, so we are saving 11. Like, this is how I can put it.
so
So
basically we are saving resources because in this case we will need only an 11-bit bus instead of 22-bit bus.
So what we are saying is that in DRAM, because you want to reduce the total number of pins, therefore you do not send out the complete address for the word that you want to read in one go. Instead, you first send the row address, and then on the same bus you send the column address. And since it is the same address bus, to maximally utilize the bus, you want to send equal number of bits for row and column addresses, so that no available resource is wasted. And it is in that context that we say that the array is therefore in a square. Logically, it is a square. The number of rows is equal to number of columns there. Where else in what other pin do we do the similar trick in DRAMs? In fact, that is what leads to this thing of what do you say, early read and early write, or all that. So which one is that?
Same
Which is the
data,
other?
same data bus for in and out.
Same data bus for input and outputs. And then we have output enable pin, which helps us to move from output to input mode or vice versa. Depending on at what time the output pin is enabled, we could have early read or we could have late read. Is this clear?
Sir, I have a doubt. In the precharge, we are precharging to bitline and bitline bar, and we are connecting only bitline to one cell. Where is the bitline bar is connected? I'm not getting this.
So where did we say we precharge bitline and bitline bar?
Like generally, we in the SM set we saw
that is an SRAM. DRAM only has one bit.
Then how do we connect to the sense amplifier for comparing to?
So we could use a single init sense amplifier just like in a ROM.
And also in the one slide when we are talking about the pages, right? So we have connected sense amplifier between 128 KB to, like, why do we do that thing? Not understand.
So you have the answer. Actually, you're asking the question and you have the answer. You already noticed where the answer is.
I thought कि बिटलाइन बार जो है वो दोनों के बीच में कॉमन, लेकिन वो सेंस नहीं हो रहा है मुझे कैसे वर्क कर रहा है वहाँ पे सिस्टम.
Okay, we'll come to that in today's class itself. Very good. Thank you for bringing up this question, Moin, and we will discuss it in a little while.
Okay.
So any other question, anyone?
So I just want to ask one more thing. You explained that the TCAS is lesser than TRAS for the row address trope and column address. So why is that happening?
So what did we discuss about this in the last class? What do you remember?
So
Because we discussed in detail why this is so.
Yes, sir. You just said a sentence like after that almost all the decoding happens. We just at the sense amplifier and we just need to do a bit of decoding and it will give us the output.
Yeah. So Faisal, we did I showed you various paths, A, B, C, D, E, and F, different paths, and we said row access delay would include A, B, C, D, and F, and the column access delay would include only E and F, and so on. You remember?
So actually that part of like the last 7 minutes, I didn't watch it again. That's why I got confused. Yeah.
We did discuss that.
Yes, sir.
Yeah, we already discussed that aspect.
Okay. Okay, sir.
Okay. So then we move to today's class. This is the second session on DRAM design. So what we were looking at in the last class was until timings. We looked at early read, late read. We'll do a quick review of the timings again. So first thing is that when you want to access a DRAM, DRAM array is organized as a square. We already discussed that. Then, in addition to that, the DRAM array, as many number of bits we may have, that many number of arrays would exist. So it appears like a cube. It appears like a n cross n cross m cuboid. As many number of bits, as many pages would be there. And we are able to read and write all the m number of bits at the same time. However, each m bit access requires one RAS cycle, that is row address trope cycle, and one column address trope cycle. Is this clear till here?
Yes, sir.
Then there are these timings that we discussed. The row RCD, the row cycle delay, the column address delay, the read address access time, the precharge time, the read cycle time, and the column cycle time. And then just give me a second. So my system is playing some pranks today. So any questions still here? How do you think we would precharge bit lines to VDD by 2? Over here it is written that bit lines are precharged to VDD by 2. How do you think we would do that? How do you think we would precharge to VDD by 2, the bit lines? If you were to do it, what would you do?
So do we have to put a voltage regulator in between the source and the bit line?
Level shifter.
Okay. Could there be a simpler way?
Previously, we have seen Q point stabilization thing in the SRAM. So we can use the same structure of that thing over here to maintain it to VDD by 2.
You're talking about Q point stabilization. Okay.
Yes.
So can we put a resistance which will give a equal resistance at bitline? So it will act as a voltage divider and VDD by 2.
What about power consumption at that time?
Yeah, power consumption will increase because of that resistance.
Won't work, na?
Yes, sir. Yes, sir.
So see, whenever you think of a solution, think of all the three aspects: power, performance, and area. You cannot
Yes,
simply say कि functionality आ गई तो हो गया. As designers, you have to look at all the various aspects linked to the circuit there. So think about it. We'll come to the answer in a little. The answer would also be interesting in the. So these are kind of linked questions. How do you pre-charge bitline to VDD by 2? How do you ensure that you have a reference bitline, because the cell only has one bitline? So how will you bring in the second bitline to the sense amplifier? All those things. So all those things you have to think about. Continue to think about that while we are proceeding with the class. So we also discussed that, okay, there is a memory controller, there is a memory chip or processor, and there would be, so there's this processor, there's a memory chip, and through the memory controller, the processor would send information to the memory chip, get the data in there, and all this paraphernalia plays around. We had looked at the delays, total delays, where we said that for a memory which has 20 to 50 nanoseconds of delays, the overall CPU latency that they will observe will be of the order of 200 to 250 nanoseconds. You remember? Because there is a memory controller in between, there is a lot of sequencing that needs to be done, synchronization that needs to be done, because of which the delays actually increase quite a bit. Are you with me? Hello?
Yes, sir.
Yes, sir.
Okay. So now it means that the delays are bad and we somehow need to improve the performance. So what is done is, see, at any point of time, I anyway access the entire row. Once I select a particular row, all the sense amplifiers for that particular page will read.
Yes,
Are you
sir.
with me? Similarly, now there are M pages. So for all the M pages, these N columns would have been read. So in fact, by the time the read operation completes, I have completed, actually accessed M cross N cells of the DRAM.
Yes, sir.
If I say that, again, using the property of locality of reference, that typically data of a program or an image would be shared or would be stored in consecutive locations, then in fact, I have actually accessed M cross N bits of one particular feature. And that can be made available to me in terms of sense amplifier latches or whichever way you want to look at it. I've written the term N cross M SRAM. So because that is, we're talking about latches. These latches could be sense amplifier latches also, or I could just put additional latches there somewhere, so that I have M cross N bits of data available with me in the output plane. And then as I want to access subsequent words, all that I need to do is, so first I gave a row address and the column address to get the first word out. Then I only need to change the column address and I will get the remaining N words out, or remaining N minus words out. This access is called as burst mode or fast page mode. So what has happened? Even though my RCD, everything was very high, my finally peak bandwidth or peak access rate is dependent on TCAS only. And this is faster, much faster than if I would say that my access time is TRAC. So the first mbit access is TRAC. The subsequent ones are TCA. Are you able to see this?
Yes. But just to clarify one thing, as you have said in the previous lecture, the TCC is the time between two CAS.
Yeah, so you call it as TCC then.
Okay. Okay, sir. Thank you.
Okay. So let us look at this example. Let us say, hello.
That N cross M SRAM is additional to that caches, or is that a cache only?
So I said this could be, I'm calling it an N cross M SRAM. This could be a set of, actually, it could actually be an N cross M SRAM, or it could simply be sense amplifier latches, which I say are kind of storing data for that period of time.
It could be additional to cache also, right?
It could be additional to the DRAM also. Okay.
Yes, sir.
So now let us say that there is a 16-bit cross 1M DRAM, and there are 4 numbers in the package. So the total, so this is one DRAM, and it is saying there are 4 numbers in the package. So if package has 1 DRAM, 2nd DRAM, 3rd DRAM, 4 DRAM, all stacked one over the other. Physically different dies stacked one over the other. And now the question is, it also gives the, what do you say, read cycle time, read write cycle time, and page mode access time, and everything it is given. Now, what is the bandwidth for one word? You have 64 bits in each word, so 8 bytes upon 110 nanoseconds. The bandwidth is only 69.35 megabytes per second. If I were to access another word, 2 words, then so 110 plus 40. My bandwidth at once jumped from 69 to 101. That is almost, let us say, 45% increase in bandwidth. And if I want to find peak bandwidth, then do you realize that I'm actually able to read 8 bytes every 40 nanoseconds? So my peak bandwidth is actually 190 megabytes per second. And the maximum sustained bandwidth, because I have a 1 megabit page, which means I have 256 rows and 256 columns. If I have 256 columns, I can access, so the SRAM down below would be 256 cross 64, because 64 bits are there. So I can actually access 256 64-bit words in one row access. So if I talk of maximum sustained bandwidth, then there are 256 words of 8 bytes each. Total time taken is 110 nanoseconds for the first read and 40 nanoseconds for the remaining 255 reads. And sustained bandwidth is 189.43 megabytes per second. You see the transition from 69 to 189. That is the benefit of burst mode or fast page mode. Any questions?
One package have 16 bits, 4 package have 64.
One package, one die. One die has 16 bits. So there are 16 pages per die. And there are 4 such dies on the inside the package. So 64 bits can be accessed.
So at a time, I am accessing 256 cross 64 bits.
Yes. Is it okay?
So in the last expression, we have taken 256 words only because we are considering one single row. Like in a row, we are changing the columns, right?
Yes.
Okay. Okay, sir.
Okay. Anything else, or is this clear?
So this bandwidth is indicating the output of DRAM. Like anyway, the bandwidth which is coming from DRAM to processor will be 1 bit only, right? In each cycle,
Why?
16 bit only. Because
Why? My data bus
bus
is,
is 16 bit, right?
see, I have said that I wanted a 64-bit module, so I could have a 64-bit wide data bus, no? Why would it be 16 bits?
Each die will have data bus, so 64
Yeah,
bit.
but the package has 4 dies in it, so there are 64 pins that the package has. है ना?
सर the processor output data जो data bus उसका होगा वो तो 16 bit ही होगा शायद ना, but if
क्यों
it
होगा?
wants to access only one die.
No, who said one die? So this is okay. So let us go into a little more detail of multi-die packages. We talked about it in DVD, I think. I do not distinctly remember. In multi-die packages, what is done is there is a substrate, okay, which has all the pins there. These are what are soldered onto your PCBs, okay. And multiple dies means that each die would have its pins connecting to different package level pins. Okay. So if I have a 64-bit module, it means there were 64 pins available. Die 1 connected to 16 bits, die 2 connected to another 16 bits, die 3 connected to another 16 bits, die 4 connected to another 16 bits. So 64 bits are accessible in parallel. Otherwise, I would not have called it a 64-bit module. No?
Yes, sir. I thought they are different one app memories. They are in single chip, right?
Yeah. Single package, single
Package.
not single die. There are 4 different dies. Is this clear?
Yes, sir.
Okay.
Sir,
Yes.
sir, here first we need to do a row decoding, and then after that we can decode the column addresses. So we will need maximum sustained bandwidth. What is the significance of this peak bandwidth?
Peak bandwidth is the bandwidth that you would require in your buffer, for example. If you have 2 different frequencies interfacing at some place and you need a buffer, so the peak bandwidth is what you would require to decide the depth of the buffer there.
Okay, so it's just like that, the maximum bandwidth that it can go.
Yes.
Okay, thank you, sir.
Okay. So now that was one way to look at it. We said that there is a simple organization. CPU needed 64 bits, and 64 bits were available in the cache, and 64 bits were available in the memory also. However, there could be multiple ways in which performance can be further improved. So we already saw burst mode improves performance. There are other ways to improve performance, which is we say we will use a wide memory. What does that mean? That means that CPU needs, let us say, 32 bits only, but my cache and my final main memory would have 64 bits or 256-bit words. So I access only one word, but that word is so wide that in reality I'm accessing 2 or 8 or many more words. You remember the concept of line length when we were talking about L2 caches? That how many words would be there in one line? Hello? Caches वाला भूल गए सामान?
Yeah, block length, right? What we are bringing.
Block size, yes.
Yes.
So this is that example. where we say that L2, even L1 cache has a line length of 4 words. So 4 words are accessed in every cycle. Out of those 4 words, depending on the multiplexer, like which of those 4 words is required by the processor, some address bits will go into the multiplexer there, and the CPU would get the access to that information. And then from cache to memory, it is the same very wide bus, let us say 256-bit wide bus. The problem with this approach is that your L1 cache has also become very wide. So it starts to become slow. Whereas the purpose of putting the cache in between was that the CPU should be able to get data much faster. So this is not really the best way to design. The best would be if I could mix both of these and arrive at what we call as interleaved design. So CPU to cache, same bus width. If it is a 16-bit processor, then 16-bit bus width. 64-bit processor, then 64-bit bus width, whatever it is. Cache then goes through the memory controller and can access multiple banks. And that multiplexing happens at the memory bank to cache transfer level. So the four modules example that we just saw, it is something like this. That we had, suppose a CPU was 16-bit, cache was also 16-bit, but I had 4 modules of 16-bit each. And they will all be accessed, all the 64 bits will be accessed in one row and transferred to the cache through this bus. Is it clear?
Sir, in wide wala option, what we are doing, we are increasing the word per row so that we can read more words.
Number of, so in wide, what I've done is that if my word width was 16 earlier, I increase the word width to, let us say, 32 or 64. So when I read one word of the cache, I'm actually reading 2 or 4 equivalent words for the CPU. Is that okay?
No, sir. Understanding this, we are increasing the size of one word.
Yes.
And we are getting this word from memory to cache.
Yeah, cache also has a wide behavior there. So cache is also wide.
Okay. Its length also will increase accordingly.
No, actually the length would reduce. In the wide implementation, line length is actually what do you say?
If it was getting 4 words, it will get 2 words if I increase the word size in memory.
Okay, so if you want to put it like that, what you are then imagining, or what you are then saying is that my CPU is 16-bit, my cache, L1 cache, you are saying is 32, and this is 64. Is that what you're saying?
Yes, sir.
Yeah, in that case, you are right. But if this was 16, then I would rather say this is 16, 16, 16, and 16. Okay.
Sir. So, like, I'm not able to get on what basis we are improving the performance, or on what basis we are measuring the performance. Like, how quickly memory is giving the data to the cache, or how quickly the CPU is fetching the data.
So you tell me. We looked at the. I think this question was also in the midsem exam, na? That there is some hit rate, some miss rate,
yes,
and
sir.
then there is some time to access data. And if you can fetch much more data in one go, then the overall time to access data reduces, overall bandwidth improves, their performance improves. We did all that.
Yes, sir, yes. From
What's the
memory to
confusion
the,
here?
I got like I'm not able to see the performance gain. Can you
So what
please
was the
share?
performance gain if my final, let us say, L2 access time was lesser? Because I have 4 words available to me right away. Instead of
Yes,
one
sir.
word, I have 4 words available to me right away.
Then
So
there's
first word will take some time, but the remaining 3 words are right there. Multiplexer delay is the only delay there.
okay.
Performance has
Yes,
improved, na?
yes, sir. Yes, sir. And for the interleaved parts, sir.
Interlude part, over here, you are getting a larger line into the cache. Writing into the cache from the main memory to the cache may take a little longer, but that's not a problem because the first word you would have anyways received first. By the
Yes.
time the request for the next word comes, the next word and third word would also already be written.
So we have like we are readily available with more number of words.
Yes.
Okay. Okay. Okay,
Same
sir.
same thing as burst mode.
Yes, sir. Yes, sir. Yes. Now it is clear, sir.
Hmm?
Thank you. Thank you, sir.
Now this is not where, or this is not fully satisfying to designers just yet. So what we also did was that when we were interleaving the memories, instead of initiating access after D1 is fully available and everything, D1 is reset and everything, we say that let us start to access in a staggered manner, such that when I start to access bank 0 again, by that time its earlier operation, pre-charge operation, has already finished. See, if it was one bank only, then my next row access would be starting only after a long time, after pre-charge has happened and something has happened. Next row kya? Next column access bhi karna hai, so there was some additional delay. There was TA plus then T reset for the column that was there. है ना? So when we interleave memories, because we now have independent arrays, we can utilize this pre-charge time or whatever reset time of any bank is to access the same information, same words from the other banks. So my overall throughput increases. Is that okay?
So basically, just like pipelining, we are accessing
Yes.
these memory banks
Yes.
within that time frame.
Very good. Yes.
Okay.
Sir, earlier, just the last few slides, we talked, we will access all the banks, all the dice at a time.
Mm-hmm.
So here, what we are doing here, accessing banks in a same. Okay, it's a bank, right? In the same die, we are accessing bank in a different time.
Yeah. Okay.
Yes, sir, got it.
So now let us look at how the performance improves in all the 3 cases. For the simple case, if you have to access 4 words, what would you need to do? 4 into 1 plus 10 plus 1. 10 is the cycle time and 1 cycle for sending data to and from the memory. So 1 plus 10 plus 1 into 4. If it was the wide memory, then the total delay would be 1 plus 10 plus 1. However, if it is an interleaved memory, then 1 plus 10 plus 1 will be there, but the other 3 words will be accessed without any extra penalty, just 1 cycle penalty, and therefore this is 15. And how would you place the addresses? 0, 1, 2, 3, so that you need to access the second row on the same page only after 4 addresses have been read. So there is a reduced constraint on time that you take to reset, time that you take to pre-charge, and you can reduce those sizes, you can save power, you can do many more things in this additional bandwidth that you have. Is that okay?
I'm not able to visualize this example. Can you please elaborate it a bit more?
क्या नहीं समझ में आ रहा बताओ?
सर जैसे इंटरलिंक में हम बात कर रहे हैं कि एक वर्ड हमने एक फेच कर लिया, उसके बाद 3 जो है हम लोग उसके सिर्फ एक ही साइकिल लगेगा उसमें। सिंपल में हम, अच्छा सिंपल में ऐसा हो रहा है सर, वाइड वाला बता दो। हाँ वाइड वाला में कंफ्यूजन हो रहा है बस।
Wide wale mein all the 4 words are readily available because the bus width is memory width is 4 words.
यस सर, यस सर, यस सर, यस सर। और सिंपल वाले में ओके, ओके सर, ओके, अंडरस्टूड सर।
Sir,
Mm-hmm.
sir, if we compare wide and interleaved, so in wide we are using greater width of cache and bus and getting lesser time.
Yes.
But in interleaved we are using lesser width of cache and bus and still getting the equivalent time using this increasing bandwidth.
Yeah, equivalent means similar order, not
Okay.
equal. है ना, 12 का 15 तो 20% तो फिर भी बढ़ गया टाइम, 25%.
Yes. सर बट अगर हम मतलब ज्यादा उस मोर नंबर ऑफ उसके लिए देखेंगे तो आई थिंक सिग्निफिकेंट इंक्रीज नहीं होगा.
That is the peak bandwidth that we could talk about, or peak sustained bandwidth that we could talk about.
ओके सर.
So the challenge between, or the comparison between the two is, for wide memory, it is a huge cost. That many extra pins need to be there. There is a multiplexer that needs to be put between cache and CPU, which may lead to more delays. Interleaved, on the other hand, is not as much area increase. Each die is smaller in area, so each die has a better yield, and all those things. The only challenge is, if you want to expand the memory by little amount, just let me add just 2 gigabytes into this 128 gigabytes memory. That will not be possible, because in interleaved memory you have a very clear defined structure, and then you go to this.
Diagram क्या है sir?
Sorry,
what is this diagram? I am not.
this diagram.
So because we already have this defined structure, so change in the memory is quite difficult in interleave.
Yes.
Okay. Okay, sir.
Okay. So another set of innovations happened, which so that was one aspect. Another set of innovations happened where at around DQ. So this was, let us say, simple DRAM. You would send row address and column address. There will be valid output for some time, and then you would, in which duration you will reset the memory, and then you would send the next row address, the next column address, and so on. This is the simple DRAM. However, if I say that there is this additional SRAM array in between the DRAM and the multiplexer, then what happens? Then I would access one row, get all the data of all the columns or all the 256 words in one go, and then I would just need to change the column address over and over again to get the remaining 255 words. This also we saw. This is the fast page burst mode access. Okay? I'm just showing it to you in terms of timing diagrams differently now. Now, further improvement of fast page mode. How do you do that? You say that while my old data is still valid, I have sent the new column address, and since I had sent the column address earlier itself, my next access will happen faster. Look at this. Only after old data was no longer valid, I sent the row address strobe or the column address strobe there. Over here, we are saying, as soon as I have finally sampled, let us say, valid output, I can switch over to access the next valid output. So I can update the column address also within the cycle. Is that okay?
That time it will not affect to valid data out. Like थोड़ा सा भी अगर पहले आ जाए next column address, so it will affect it.
Yeah, so that is what we'll define as. So what do we call that timing? T hold. We have two timings, T access and T hold. T hold means what is the minimum duration for which my previous data will be valid after the new address trope comes. So that is a function of hold time. If that hold time is less, then this gray region will shorten. If that hold time is large, then whether this gray region shortens or not doesn't matter. You know that you're able to access faster.
Sir, I want to clarify, like in the row address, when we give the row address, that row will be decoded and sense amplifier का sense भी आ जाएगा, so that एक row का जो complete data होगा, that will be at sense amplifier terminal.
Yes, that is latched either at the sense amplifier level or at the layer of this n cross m sense memory SRAM.
ओके, सो जो हमने फर्स्ट टाइमिंग डायग्राम देखा था ना सर, जिसमें हम रो एड्रेस दे रहे थे, कॉलम एड्रेस दे रहे थे, फिर रो एड्रेस दे रहे थे, वहां पर व्हाई वी आर नॉट अगेन वी आर गिविंग कॉलम एड्रेस, लाइक सारा तो सेंस एम्पलीफायर के पास रेडी है ना, व्हाई वी आर अगेन गिविंग रो?
This could be fully random access, na?
Okay.
I needed just one word and then the next word that I needed was in a very different place.
So यहाँ हम वो कंसीडर नहीं कर रहे कि सेम रो रीड कर रहे हैं.
रो तो सेम, हाँ, सेकेंड साइकिल में सेम रो एड्रेस आ रहा है, वो हम नहीं अज्यूम कर रहे. जबकि हम यहाँ कह रहे हैं कि टिपिकली आपका जब डेटा होगा तो बर्स्ट मोड एक्सेस उस पर काम करना चाहिए लोकेलिटी ऑफ रेफरेंस की वजह से. सो आपको खाली कॉलम एड्रेस चेंज करना है, या आप उस कॉलम एड्रेस को भी और जल्दी चेंज कर सकते हो टिल द टाइम योर डेटा रिमेन्स स्टेबल इनसाइड द मेमोरी. That is defined by T hold and T access.
Sir, here we are talking about reading the burst operation, reading same row.
Yeah, same row that has been accessed and is now available in the SRAM. When do I initiate the next read? On the SRAM there.
अगर हम ये एक्स्ट्रा SRAM वाली जो चीजें हैं वो इफ वी कनेक्ट, इवन दो इफ वी आर, अगर हम अलग अलग रोज रीड कर रहे हो, then we have to give row address, column address, validate, then again
Yes. So even in this EDO DRAM, if the addressing is completely random, you go back to the original first case. Are you able to see this? That you at once go back to the DRAM team. So this is still further where we say that I do not need to send addresses again and again and again. I would rather have a clock signal. And then at every clock, I will initiate the new access. So valid data comes much, much faster now. Hello?
So here we are fetching the data from a row only, like we give a row address.
Oh yes. ये देखो ना, एक ही बार रो एड्रेस दिया एंड देन एक बार ही कॉलम एड्रेस भी एक ही बार दिया, उसके बाद इंटरनली ही इंक्रीमेंट कर दिया कॉलम को, saying that column address will change only one by one.
Yes sir, yes. Okay.
So now with the speed aspect taken care of, we look at how to design the reference. The question that came earlier in the class, कि bit cell की तो एक ही bit line है. How do you get the reference bit line? So what we do is, in a typical DRAM, we would use a level restoring sense amplifier. What does level restoring sense amplifier mean? It means that there is no pass gate in between now. So the sense amplifier is connected and coupled with the bit line at all times. Are you able to see this? When the sense amplifier will operate, the bit lines would go to 0 and 1.
So how this sense amplifier operation is happening? Can you?
So how does the regular sense amplifier operation happens? Can you describe that? I will then tell the changes. What do we do in a regular sense amplifier?
तो यहाँ पे बीच में हमारे पास गेट होते थे, फिर उनको हम लोग हाई करते थे तो हमारा बाहर वाला बिट लाइन का डेटा सेंस एम्पलीफायर में लैच हो जाता था। फिर
नहीं 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 नहीं, नहीं। यहाँ पे पास गेट होते थे. You would turn off these pass gates and
हाँ
turn this one on.
हाँ सॉरी सर, यस
When you turn this one on, that was when latching action happened.
यस सर। अच्छा मैंने टाइम
Exactly the same here also.
से, लेकिन वहाँ यहाँ पे तो हम लोग का कनेक्टेड ही है सेंस एम्पलीफायर से दोनों बिट लाइन, और वहां पे हम लोग पास गेट्स ऑफ करके ये सेंस इनेबल ऑन करते थे, ऐसे ऐसे ऑन करते थे। तो यहाँ पे अब ये कनेक्टेड है तो किस तरीके
That
से?
is connected. That is why it is called level restoring. बिट लाइन पे 100 मिलीवोल्ट का डिस्चार्ज हुआ, लेकिन आपने उस 100 मिलीवोल्ट के डिस्चार्ज को सेंस कर लिया और उसको पूरा 0 तक ले गए.
ओके ओके
आपने, और जब आप इस तरफ को पूरा 0 पे लेके गए तो क्या हुआ? साथ ही साथ DRAM सेल के अंदर जो कैपेसिटर था वो भी पूरा का पूरा चार्ज स्लैश डिस्चार्ज हो गया.
यस सर।
आपने रिफ्रेश साइकिल भी साथ के साथ चला ली बाय यूजिंग दिस काइंड ऑफ अ सेंस एम्पलीफायर.
ओके यस सर। सर ये वाला भी एक डाउट था कि ये रिफ्रेश, हाँ अभी वो भी क्लियर हो गया। ओके सर।
ठीक है. तो ये सेकंड बिट लाइन कहाँ से आएगी? तो इसको बनाने के लिए मल्टीपल तरीके करे जा सकते हैं. वन थिंग कुड बी दैट फॉर द सेंस एम्पलीफायर यू से दैट alternate rows will, the bit lines connected to alternate rows will be called bit line. Bit line connected to the other alternate set of rows will be called the bit line bar. Okay, and now both are connected to the sense amplifier in between. One acts as a reference, the other acts as a, so which one would act as a reference? Let us say I am selecting, so for my particular read operation I selected this particular row. So let us say this was row 0, row 1, row 2, row 3, 4, and so on. So which bit line, or where do we now get the reference from? Let us say row 0 was the one that was selected. It means this side would discharge if there was a 0 stored here. The problem is if this does not have, or if the, how do I put it? We'll come to that later. So the thing is that you access one row and the remaining rows act as the reference. So one bit line, second bit line. There are two bit lines and they act as a reference.
So when bit line come, either bit line or bit line bar will be selected. So whichever is not selected will act as a reference.
Okay. Yes. ठीक है ना? So each BL acts as a reference for the other. This was the patent by Mitsubishi. So what did others do? Others also said that, okay, let us have a dummy cell somewhere. And if I am selecting this bank, that is, let us say I am selecting this particular cell, then the reference would come from this bank, the other one. Is that okay? Are you able to see this? So you've generated a reference again, but now from the bit line on the other side of the array. So जो हमने, you know, you're talking about that there is this kind of an organization of pages. यहाँ पे 128 के थे, यहाँ पे 128 के थे. They were sharing the sense amplifier. This is how they were sharing the sense amplifier.
Yes,
Is
sir.
it okay?
Yes, sir.
So now, any further questions here?
Yes, sir. वो sense amplifier पर लाइक उसका ऑपरेशन वो जो बिटलाइन है दैट इज कनेक्टेड टू प्रीचार्ज वाला पॉइंट इंटरनल नोड को हम जो प्रीचार्ज कर रहे हैं लाइक अर्लियर वी हैड डिवाइस टू डिस्टिंग्विश बिटवीन देम अभी इंटरनल नोड प्रीचार्ज एंड बिटलाइन प्रीचार्ज एक ही हो गया लाइक दे आर शॉर्टेड राइट
Yeah. In DRAM, yes, that is what happens. As you read, the refresh also happens simultaneously.
refresh not I'm talking about the pre-charge like bitline को जो pre-charge कर रहे हैं and in SRAM bitline pre-charge and sense amplifier का internal node pre-charge they were two different things like sometime difference was there.
Oh yes, because there was an internal node in the sense amplifier. This sense amplifier doesn't even have an internal node. So दो अलग-अलग pre-charge की तो बात ही नहीं आएगी ना, है ना? Any questions? Clear?
टाइमिंग ग्राफ्स एक्सप्लेन कर सकते हैं जैसे आप जो जो टाइमिंग वो था ना सेंस एम्पलीफायर की स्लाइड में
So your bit line and so you first equalize. Okay? Equalize में क्या होगा? आपने एक bit आप पिछली cycle में you had let us say taken one bit line to VDD, other bit line to 0. You say I will equalize. As soon as you equalize, what happens? VDD and 0. Both the bit lines have same capacitance. So what is the voltage at both the bit lines then? Are you able to see that VDD by 2 generation doesn't really require a charge, doesn't really require a regulator or a potential divider or anything?
but you have connected the supply VDD by 2 how do we get that is the question right
I'm sorry?
that the equalizer रिचार्ज को जो
हाँ,
हमने सप्लाई दिया है वो VDD by 2 दिया है राइट
कहाँ दिया है?
प्रॉपर कुछ लिखा है ना VDD by 2
Oh, one bit line means differential is VCCS by 2. That is something else. So that has become overlapped. Don't worry about that. So what we are saying is that if this was due to sense amplifier operation, this was charged to 1 and this was charged to 0. When you will equalize, what happens? Both become VDD by 2.
Yes, sir. Due to equalization, both of them
Charge
become
sharing. Due to charge sharing.
Yes, sir. Yes, sir. Yes.
Okay? You do not need the regulator at all.
Yes, sir.
Then you would give the word line. So once the word line comes, depending on whether your memory cell had a 0 or a 1, the one of the bit lines would rise or fall a little. SAP will go high, SAN will go. So SAP was high, it will start to go low. So this PMOS turns on. SAN was low, it starts to go high. So this NMOS turns on. So what that means is that this latch is now operational. Are you able to see this? As soon as the latch operation starts, I will distinguish between 0 and 1. Then at the beginning of next cycle, I will initiate equalization again.
Sir, where is the bitline charging वाला part? ये equalizing part ही bitline pre-charge हो गया, right?
Bitline pre-charge. दोबारा से बोलो.
Bitline pre-charge and equalizing process ये
same है.
ही है, right?
Yes.
And what are these extra capacitors CP, CCL?
Oh, they're just shown to represent the bitline capacitance there.
Thank you.
So that is how the replica path or the reference bitline is designed. Now we come to another part, which will then lead us to non-volatile memories also, which is the charge pump. What is a charge pump? What is a charge pump? No one has heard about charge pump earlier? Okay. So charge pump is a circuit which increases voltage from the levels that are available. So I have a voltage available, which is 1 volt. I can generate 2 volt, 3 volt, 10 volt output by using 1 volt. Similarly, I have something available as ground, and I could generate negative voltage on the ground. That is also a charge pump. Now, those of you who are working on the negative word line, negative bit line right driver, can you sense something? What could be a charge pump? What could a charge pump look like?
Some circuit with capacitor.
There is a capacitor which stores charge, and then that charge is pumped onto another capacitor, due to which the voltage between the plates of the other capacitor rises very much. The extra charge has pumped up the voltage. So this is how it would appear. So there is a capacitor, there is another capacitor, and it is the interplay of these two capacitors that leads to, or that results in, a V out which is higher than what was V in. How do we do that? So we divide the operation into multiple phases. The first phase is, let us say, charge phase. So what is done? In charge phase, S3 and S2 are closed, appear to be like resistances. So what happens? There is a charge that flows from V in until this side, and the charge from the other side of this capacitor goes to 0. So capacitor CF is holding some charge onto it. Some voltage would appear. What voltage? That would be equivalent to Vn, or a little drop around it, but finally stabilizing at Vn. Okay? Then we move into the next phase, which is about charging. Then we move to the next step, which is about charging the C out. So अभी तक हमने क्या देखा? Charge phase में Vn एक तरफ लगा, and this kind of a path was created. In the next phase, what we do is we discharge. What does discharge mean? Now I close these two resistances, these two switches, and I open the ones that were closed earlier. All of a sudden, what happens? This plate, which earlier had a 0 on it, now at once has a Vn on it. What does that mean? Because we know that this side has much more charged, was more charged. So this plus Vn goes to 2Vn. Okay? And this Vn or this CF, this node is connected to V out. So we can actually say V out is approximately equal to twice Vn. Are you able to see this? What have I done? I first stored charge onto this particular capacitor, and then I changed the charge of the voltage on the other side, other plate of the capacitor, so that this charge could now be pumped onto the output capacitance or the output load. Is it clear? This is the new circuit, the red one. let us look at it in terms of a time series. So that was just one step में आपको लगा कि सीधा VDD to VDD आ गया. Doesn't really happen like that. In reality, when the charge pump starts to operate, then the voltage VGG over here, which we say is the V output voltage, would see this kind of increase, a stepped increase, and then almost becoming stable. The black curve. How is it operating? Who can explain? सब कुछ सामने है. चलो, let us say ring oscillator gave a output 1. So what happened? The C was initially 0, it will go to 1. Until it has gone to 1, this transistor is off. And D would go to 0, from 1 to 0. So this transistor is off. So this side of this node holds the earlier voltage only, earlier charge only, and the other side has discharged to 0. What happens? There could be an impact around the diode. Okay? Otherwise, you would transfer some charge to this particular capacitor VG, and then you would change the voltage of the other plate so that you have 2 VG available to you. 2 VG will not come instantaneously, it will come over time. Is it okay? Are you able to see the functionality? Is it clear? Hello? Any questions? Friends, is it clear?
So if we add more inverters, the charging phase will increase. So it will quickly go to that, right?
Yes. If you add more inverters, charging phase would increase. We could probably have a slightly higher rise per cycle. We could probably rise a little higher per cycle. But the thing is that you want to be fast, so higher per cycle, but that would take a little longer. So I will have more number of cycles that I would need. No, fewer number of cycles, but the cycles are larger in themselves. Over here, we have used fewer inverters, so every cycle is short, but I may need more cycles to go to the desired voltage level. Okay? So what is happening is, I say that there is this VGG. So this is the equivalent circuit there. There is a capacitor CS, this one, and this capacitor shares the load or pumps the charge onto the load capacitor, which is much larger. And overall, the timing improves. Is this okay?
Yes, sir.
Great. So again, we will come to approximately 2 V high after some time. So we will stop here. We will start with non-volatile memories in the last class. If there are any pending questions regarding DRAMs, you can ask that. If there are any questions related to projects, we can discuss those also.
Sir, in the last class, TRC, which was given 110 milliseconds. which carries precharge plus TRAS. We saw that precharge is only about equalizing the 2-bit line. So I think it's very, it will take very less time. So RAS was itself 30 millisecond, but we are 70, 80 millisecond we are taking as a precharge here, right?
So have you tried equalizing two signals, bitline and bitline bar, when you are precharging them in the SRAM itself? Let us say, forget about the DRAM. In the SRAM, there is a bitline and bitline bar, and you want to, what do you say? And you want to equalize them. You put an equalizer there. How long does it take, do you think?
No, but I think the bitline C is very high. That why is it taking too much time?
Yeah, that is definitely there. But even equalization from let us say VDD by 2 minus 40 millivolts and VDD by 2 plus 40 millivolts to VDD by 2, almost VDD by 2 on both the bit lines, means that you are transferring information across a pass gate. So this is VDD by 2 minus 40 millivolts and VDD by 2 plus 40 millivolts. So what happens? You are you are transferring charge at a VDS of approximately 80 millivolts. This is still fine VDS. As this becomes 30 and 30, it goes to 60. As it becomes this VDS goes lower, the total time it would take to charge would increase because VDS is low, so the current that is flowing has reduced. Is that okay?
Yes, sir. It's experimentally, if we see that will be more clear. Like if the difference is small, that will take lot of time to equalize.
Yes. Hana? Anything else?
Sir, in the early read operation in the last lecture, we saw that CAS will come later, but there was a junk because the output was high. So how that will be distinguished from junk, data out and junk? Like output was high, no?
So junk you don't bother about. You simply latch output only after T access.
But memory is giving output based on o output access time, right?
Yeah. Memory could be giving output wherever. But when do you latch the memory output? That is what is important, na? Memory output will be latched somewhere. Either in the next stage of flip-flop, somewhere it would be latched. At the system level also, you will need to latch memory output, na? Somewhere.
Yes, sir.
So you do that after access time. Then there is no problem of whether there was junk before the access time or not. Is it clear?
Controller has to work like जब CS आए तभी output ले.
दोबारा से पूछ रहे थे, बता रहे थे, मुझको तुम्हारे टोनालिटी से समझ में नहीं आया.
OE जो controller होगा that will look for OEL, right? The chip output chip enables वाला signal. कि अगर
Yes.
वो on हो तो it should take the data from memory,
Yes.
right?
Yes.
But वो time पर CAS on नहीं है. CAS is a internal signal of memory.
हाँ.
तो
That is
जैसे
okay.
OEL आया तो memory controller will start taking the output जो भी दे रहा है वो, right?
Yeah. So you will bring.
जंक आ गया ना.
You will either bring OEN after the output is stable, let us say, which could be called as late read, or if OEN was all low already, then there would be some junk on the output, but you will latch the output only later. ON is only output being driven to the bus, to the output bus. Output bus would also latch it somewhere. That latching should happen after the total access time has elapsed. Is that okay?
Yes, sir.
So anything else? Even questions related to projects are fine. How are your projects coming along, by the way? Have you picked them up again after the mid-semester break, or ठंडे बस्ते में पड़े हैं?
Sir, regarding the refresh, I have a question. Like in the read operation, refresh is anyhow is going to happen. So जो दूसरा refresh हम बात कर रहे थे कि 3 millisecond पे होगा. So it's independent of the read operation और कि last operation जब हुआ उसके 3 millisecond बाद refresh होना चाहिए. Is that
So last refresh के 3 मिलीसेकंड बाद या जो भी है. Yes.
So is there any counter? कौन manage करेगा 3 millisecond?
हाँ, कंट्रोलर के अंदर ही काउंटर रहेगा.
Okay.
है ना? So anything else?
सर मैं प्रोजेक्ट के बारे में पूछ सकता हूँ सर?
हाँ हाँ प्लीज, मैं तो कह ही रहा हूँ प्रोजेक्ट के बारे में पूछो.
सर मेरा प्रोजेक्ट है रेप्लिका कॉलम फॉर राइट.
हम्म.
तो सर मतलब जैसे कि मैंने उसका एक इंटरनल स्ट्रक्चर बना लिया है कि मतलब मैं कैसे प्रोसीड कर रहा हूँ स्कीमेटिक. तो सर क्या मैं आपको शो करूँ कि मतलब मेरे को वो दिखाना है कि मतलब मैं सही प्रोसीड कर रहा हूँ या नहीं?
शो कर सकते हो. जस्ट गिव मी अ सेकंड, आई विल अनस्पॉटलाइट माय सेल्फ. यस, प्लीज शेयर.
सर स्क्रीन विजिबल है?
हाँ हाँ.
तो सर ये मतलब स्कीमेटिक है जो मतलब जो हमने बनाया था, जो हम सोच रहे हैं कि मतलब बेसिकली हम एक क्लॉक इंटरनल लेंगे, तो उसमें बफर्स लगा के और ये आरसी लगा के हम एक डमी वर्ड लाइन जनरेट कर रहे हैं जो कि हम एक डमी रोडेक वाली टीम को देंगे. और उसके बाद हमने यहाँ पे एक मतलब 2 इंटरनल नोड्स int 0 और int 1 जनरेट करी बेसिकली, जो कि एक में इन्वर्टर लगा दिया, एक में इन्वर्टर नहीं लगाया, जस्ट टू परफॉर्म राइट ऑपरेशन. एंड आफ्टर दैट जो हमने ये मतलब int 1 से एक राइट डेट सिग्नल जनरेट कर रहे हैं, वो बेसिकली हम यहाँ से जनरेट कर देंगे इस वाली int 1 नोड से, जस्ट टू गेट दैट.
हाँ, कि अगर int 1 टॉगल कर गया इसका मतलब राइट ऑपरेशन पूरा हो गया.
राइट ऑपरेशन पूरा हो गया तो हमने राइट डायरेक्ट सिग्नल को हाई कर दिया. तो मतलब ये सर्किट ही हमें बनाना है.
हाँ.
और सर इसके लिए मतलब जो वो
ये भी बनाना है, ये भी बनाना है.
ओके. हाँ सर, इसके अलावा मतलब और क्या करना है?
इसके अलावा इस सर्किट के एडिशनल ये रेफरेंस बिट सेल बना हो गया.
यस सर. सर ये तो मतलब हम वो बिट सेल वाली टीम के साथ कम्युनिकेट करके उनके साथ.
हाँ हाँ हाँ. यस, दिस हैज टू बी डन क्लोजली विद इन कम्युनिकेशन विद देम, बट ये भी बनाना है.
यस सर. ओके ओके. मतलब सर हमें मतलब ये 2 सर्किट बनाने हैं, मतलब बस यही पता करना था.
हाँ हाँ, ये 2 तो बनाना ही है. अगर आपको कुछ और भी चाहिए तो वो भी बनाना है. मेरे से मत पूछो. ये 2 सर्किट आपका जो राइट डिटेक्ट है उसको रीसेट कौन करेगा, वो नहीं दिखाया आपने अभी यहाँ पे.
ओके
तो सब कुछ आपको सोचना है.
ठीक है सर.
है ना. नेक्स्ट साइकिल में भी तो यही चीज, यही ऑपरेशन दोबारा से चाहिए हो सकता है, तो मेमोरी को फिर किसी को रीसेट करना पड़ेगा.
बिल्कुल सर.
है ना. दैट आल्सो नीड्स टू बी शोन देन.
ओके
ठीक है.
ठीक है सर.
ओके. एनीथिंग एल्स?
नो सर.
ग्रेट. एनीवन एल्स हैव एनी क्वेश्चंस?
सर हमारा भी रेप्लिका ही है फॉर रीड ऑपरेशन. वी अंडरस्टैंड दिस कमिटी का नाम. अभी हम लोग क्या करें, लाइक वी डोंट हैव सेल, सो डू वी स्टार्ट डूइंग लेआउट विद सम रैंडम लेआउट ही बनाना है या इसमें और चैलेंज क्या है? मतलब आई एम नॉट गेटिंग दैट थिंग.
दोबारा से बोलो.
आई अंडरस्टैंड द स्कीमेटिक. उसमें रेप्लिका कॉलम फॉर रीड ऑपरेशन इज माय प्रोजेक्ट. तो इसमें SRAM होगा जो कि ऑलरेडी कोई डिजाइन करेंगे.
हाँ.
We are just need to connect it properly, like हम समझ गए कि उसको some VR के थ्रू
एंड
उसको प्रोग्राम
आपको
करना
उस
है.
रेप्लिका के साथ फिर डमी आईओ वाली टीम के साथ बैठ के आपको सेंसैम्प एनेबल बनाना है, रीसेट बनाना है. ऑल दैट इज आल्सो योर टीम्स वर्क ओनली. यू कैन नॉट जस्ट मेक द array वन कॉलम एंड से हो गया काम.
मतलब वो सेंस एम्पलीफायर को उनके कनेक्ट करके हमको बताना है, मतलब लास्ट
Yeah, you have to finally trigger the SAEN signal, na?
सो मतलब उसको जस्ट एक कुछ बफर्स के थ्रू पास करके हम बता दें कि ऐसे ही जनरेट हो गया यस, या फिर उसको एक्चुअल में सेंस एम्पलीफायर को कनेक्ट करना है?
आईओ के सेंस एम्पलीफायर पे आप एक्चुअल में पिन निकाल के दोगे अपने सर्किट से कि वो आईओ के सेंस एम्पलीफायर से वो कनेक्ट होगा? वो आपको पिन निकाल के देना है, लेकिन वहां तक की पूरी फंक्शनैलिटी आपको इम्प्लीमेंट करनी है।
सारी फंक्शनैलिटी में यही है ना कि सर एक कॉलम बनानी है, एक रो बनानी है बस, और उनको
ये
प्रोग्राम
फंक्शनैलिटी होती है, ये फिजिकल इंफ्रास्ट्रक्चर होता है।
या इंफ्रास्ट्रक्चर
फंक्शनैलिटी में तो हम ऑपरेशन देखते हैं ना, कि एक डमी वर्ड लाइन आएगी, उसके बाद एक डमी बिट लाइन डिस्चार्ज होगी, वो डमी बिट लाइन डिस्चार्ज होगी तो एक रेप्लिका सेंस एम्पलीफायर उसको सेंस करेगा, और उसके बाद वो कुछ डिले बाद रीसेट और सेंस एम्पलीफायर एनेबल सिग्नल जनरेट करेगा। दैट इज व्हाट फंक्शनैलिटी इज।
यस। सो आवर मोटिव, हमारा जो वो रहेगा वो इनपुट वी विल गेट फ्रॉम सम के सिग्नल है
So you
डिकोडर
will
पे
get some
आ
word
गया।
line. You can assume that there is a dummy row decoder which will give you some dummy word line.
ओके, वी गॉट द वर्ड लाइन सिग्नल, वी
Dummy
हैव
word
टू।
line.
हाँ,
Replica word
डमी
line
वर्ड।
signal you will get, and then you have to do everything from there until sense amplifier enable signal is generated.
In that everything we just have to discharge few number of cells which we are connecting to word line, that word line, right?
So first you have to track the word line.
Yeah.
Then you have to discharge the bit cells. Then you have to sense that discharge. Then you have to generate the reset signals.
Okay.
है ना? See, replica bit line, even though it is a full string bit line, it also is not a digital signal. Do you realize that? It has a slope which could be very bad.
So it's all about the timing के वो लोग को
Yes.
जितना टाइम लग रहा है, that we have to replicate
The
here.
entire purpose of replica path is timing. है ना?
Yes sir.
ठीक है? Anything else? Mm-hmm.
Good afternoon, sir.
Good afternoon.
So, sir, to add on a point, जो Moin sense enable signal generate करेगा, because our team is working on alpha type sense amplifier.
Mm-hmm.
तो वो सेंस एनेबल सिग्नल जो जनरेट करेगा उसकी विड्थ वही होगी ना जो हमको जिसके लिए सेंस एम्पलीफायर डिजाइन करना है, दैट इज 100
हाँ,
पीसेस।
उसकी विड्थ कितनी है वो आप बताओगे उसको, मोइन को फॉर एग्जांपल।
ओके,
है ना? तो he has to interact with the sense amplifier team, he has to interact with everyone to be able to finally arrive at the circuits inside the replica path, the total replica path there.
ओके सर, वन मोर थिंग, मैंने बिलाल सर से भी पूछा, उन्होंने बोला कि रिगार्डिंग पीचार सर्किट, जो पीचार सर्किट हमको यूज करना है सेंस एम्पलीफायर में अपने, तो सर ने बोला कि पीचार सर्किट यू हैव टू, बेटर ये रहेगा कि तुम अपना खुद जनरेट करो पीचार सिग्नल। तो पीचार सिग्नल के लिए उन्होंने बोला कि क्लॉक तुम्हारे पास आएगा और अनेबल सिग्नल भी तुम्हारे पास आएगा फ्रॉम रेप्लिका टीम। तो सर ये जो क्लॉक की बात हुई यहाँ पर, ये सर इंटरनल क्लॉक की होगी ना, तो इंटरनल
हाँ, ये इंटरनल क्लॉक होगी, दिस विल बी इंटरनल क्लॉक।
तो ये फिर हम उस टीम से बात करेंगे जो इंटरनल क्लॉक जनरेट कर रही है,
हाँ, जो कंट्रोल के सर्किट बना रही है। यस यस, so you see so much of interaction has to happen amongst teams.
Yes sir,
because it's a big macro, it's a complex macro in itself. ठीक है?
थैंक यू, थैंक यू।
चलो, गुड। Shaina, you have a question?
Sir, I don't have a question, but I just wanted to ask you something. Like in mid-sem, we had two questions, the first one and the third one. So like I have not done DVD, so I was a bit clueless as to what exactly has to be done. So in the end sems also, can we expect to have some questions related to DVD? Because
See, DVD is not prerequisite of this course, but जो भी see we have been discussing all that. जैसे चाहे वो lots थे, कि slow lot है, fast lot है, all these things we've been discussing, नहीं?
Yes, sir, but the temperature, like,
Yeah, so
how
you've been
to exactly
simulating
find it?
circuits. Chalo, forget about DVD. You've been simulating circuits.
Yes.
You know that high temperature pe the delays are higher. That all you are already seeing in MDT also.
Hmm.
Discharge rate, how does it change? Leakage, how does it change? All these figures of merit of the memory cell, you are already simulating, na?
We are aware of that, but simulation part, we haven't done that yet. Like, we'll be doing that in the project. But
See, जो DVD की knowledge है, it is not कि आपको DVD करा होना चाहिए, but this is so basic that we anyways also discuss it in this class. And if we like हम discuss करके आगे बढ़ गए, आपने अगर उस समय clarify नहीं करा, then I usually stop for clarification every now and then, is it not? Have any question ask, have any question ask, have any question ask. So कुछ भी नहीं समझ में आता तो please ask ना.
okay. Yeah, तो हाँ मेरे को बस ये कंफर्म करना था कि
मेरे लिए कोई डिस्टिंक्शन नहीं है डीवीडी में और एमडीटी में. They just are like interconnected, and कुछ नहीं समझ में आ रहा तो I am not hesitating to cover any concept that we have discussed in DVD. Am I like we've discussed so many DVD के concepts in this class also.
Yes, sir. Yes, sir.
है ना? Deepank, you have your hand raised.
Good afternoon, sir. I wanted to, sir, am I audible?
Yeah, you are audible.
Okay. So I wanted to, so actually what we were doing till now is we were generating the SAEN as well as reset. So, but you said the other team has to generate reset.
Has to work with you to generate this. Has to ensure that whatever delay they are giving is appropriate for the overall SAEN generation delay.
Right now we are modeling it. We were modeling it via large capacitance, but now we will be
have to connect it with their circuit.
Yeah, but sir, still we have to model for now. So we were planning to use a source, PWL source with a huge slope.
So since you have within us, there are teams that are also coming to a closure of their project. It is best that both the teams work together, connect, and show that both systems or both circuits are working fine together.
Okay.
Ideally, I would want that at the end of this course, हम बस clock दें, address दें, data दें, and we should be able to get Q or we should be able to write into the memory cell. Okay. That kind of interconnectivity teams must have done amongst themselves.
Okay, sir. Got it.
Okay.
Thank you.
Anything else?
Also, from April onwards, we'll be having offline classes, right?
We will have some classes offline, but because I understand that you guys love recordings, so we will see. It could be a mix of offline and online classes. There will be some guest lectures which could be offline because the guests do want to come and we visit and meet all of you. There could be others which could be online.
Okay, sir.
Okay. Chaliye. All the best, guys. See you on Thursday then. In fact, we have office hours tomorrow. So those of you who wish to join office hours tomorrow, we will meet tomorrow also. Bye-bye.
Thank you, sir.
Thank you, sir.